0.6, 0.8, and 1.0 millimeter diameter capillary tube, or an expansion valve, which I'll be able to test at different opening steps of the valve pit. The capillary tubes are each about 400 millimeters long. The majority of the pressure drop happens in the first 10 to 15% of the length, so the diameter is the much more important parameter. The expansion valve is designed for much larger systems, as you can see from this datasheet chart here, but I think it can still allow for some rough adjustment of a smaller system. I guess we'll find out. The evaporator is 20 feet or 6 meters of copper tubing wrapped tightly on the inside and outside with 4 25-watt silicone heater pads. On the outside, they're held tight with zip ties, and on the inside, I've used 3D printed wedges to hold them tight against the tubing. Then the whole thing is heavily insulated, otherwise we're not going to get an accurate result. A thermocouple is strapped to the outlet of the evaporator, so by dialing power into the load resistor with a variable power supply and reading out the steady state temperature, I'll be able to generate a graph that looks something like this, showing the amount of heat lift and watts at various temperatures. So in theory, with less flow restriction, you should get a steep line like this, and then with greater flow restriction, the line slope should become shallower but zero out at a lower temperature. Let's go ahead and put this thing together. It's a pretty straightforward matter of just swaging some quarter-inch tubes with my drill and brazing them together with some copper phosphor rod. Wait, before we continue, riddle me this. Phones, computers, AI girlfriends, and that smart fridge that you paid $5,000 for. What do these things have in common aside from being built as cheaply as humanly possible? Software, that's what. You may have noticed software is everywhere in your daily life, even in places where it has no business being. And it's going to stay that way until we all get sent back to the Stone Age by a big solar flare. If you're working in any space that's even remotely technical, you're probably going to run into a situation that calls for at least some amount of software, even if that means a few lines of code in the simple microcontroller. And that means you should be prepared by learning to code. Yeah, that's right, I said the thing, but that's because it's true. According to big tech snooping, more than half of you are Zoomers or millennials, so you need education presented to you like it's World of Warcraft and not like a stuffy 1950s college lecture in a smoke-filled classroom. Well, guess what? Boot.dev does exactly that, offering interactive tutorials for Python, JavaScript, Git, SQL Go, and several other programming languages, and it's structured like a role-playing game with experience and achievements so that it can satisfy all you kids addicted to dopamine hits to keep you motivated to keep learning. Boot.dev is set up to actually get you writing code, which is by far the best way to learn instead of just watching or reading tutorials. If you're a competitive kind of person, you can compare your learning progress against a global leaderboard, and with the new training ground feature, you can practice against AI-generated coding challenges to sharpen your skills before doing graded tests or challenges. They offer a 30-day, no questions asked, money-back guarantee, so if you try it and feel like it's not for you, you're not going to lose any money. Go to boot.dev and use promo code HyperspacePirate to get 25% off your first year if you sign up for the annual plan. Okay, let's get back to the video. One thing that's a little different than a normal system is I want to be able to take the thing apart and put it back together easily, so I'm going to use a lot of flare fittings to connect everything. So normally you'd have to connect two flares with a flare union, but I can't find any in my junk drawer. So what I did is squeeze down the NPT side of an NPT to SAE flare adapter fitting and then brazed it to a piece of quarter-inch tubing with lots of flux. It's ugly as hell, but it actually holds pressure perfectly. Obviously we need to know operating pressures for the high and low side for this test, so to install the pressure gauges I just drilled tiny holes into the tubing on both sides and snake a piece of 0.6 millimeter inner diameter capillary tubing, then wrap it a few times as a strain relief. Then I brazed those capillaries to these stubs with flare fittings and attached the gauges. And here's the 0.6, 0.8, and 1.0 millimeter capillary tubes with the quarter-inch tubes pinched down on them. And here's after brazing and adding flare nuts. And of course, there's also a needle valve for servicing on the low pressure side of the system. This is the manifold that will connect to a set of needle valves for selecting between the capillary tubes or the expansion valve. That took way too long to braze with propane. I really need to get more oxygen so I can use my oxypropane system. This is the manifold mostly hooked up. The expansion valve arrived really late in the production of this video, so at the time of filming this clip, I have its connection shut off on both ends with needle valves. I did a quick run-up of the compressor on air to make sure there weren't any flow obstructions on the capillaries, and just out of curiosity, check the pressure readouts by switching the different tubes.
most of you are probably familiar with the word acid. Most people, just by thinking about it, picture some gross green liquid that very dramatically eats through everything and seems really aggressive and dangerous. That's at least how acid is often portrayed in popular media, and from the perspective of a somewhat experienced chemist who worked with many acids before, this just makes my head hurt. You see, there is so much more to the word acid and acid in general. Some indeed can cause a lot of damage, but some also allow you to digest food or are used to grow your favorite fruits and vegetables. That's why in this video I decided to give you a little tour of the amazing world of acids and show you that they are really not what many of us think. To prove it, I am going to make one from just some plain table salt, so grab yourself a cup of lemonade and enjoy the show. Okay, so every textbook would start by explaining what an acid is and how it works on paper, but that's just plainly boring. So instead, let me show you a cool experiment. If I get some regular baking soda into a bottle along with some water and dish soap, and then add some of this mystery acid, which I will talk about in just a minute, it creates this fountain of foam, which is quite beautiful and really painful to clean. The reaction that just happened here is known as a neutralization reaction, and this mysterious acid that I used is just some extra strong vinegar, or in a more chemical term, glacial acetic acid, which I made in a previous video. This reaction, except for the stronger vinegar, is the exact same as the baking soda volcano you might have done in your school, and it actually has some really cool chemistry going on behind it. The reason why it even occurred is because acetic acid has this little hydrogen. Hydrogen atom here, which is what gives it its acidic properties. Every conventional acid has this hydrogen atom and something attached to it known as a conjugate base. The strength of an acid is determined by how much the conjugate base wants to get rid of the hydrogen, or in other words, dissociate into so-called ions. For example, acetic acid is only a weak acid because in water only a part of it dissociates, and hydrochromic acid, for example, is a strong acid because in water it all breaks down into protons and bromide ions. So, with this in mind, we can say that a conventional acid is just something wanting to get rid of a hydrogen atom in a water solution, and that's actually the hydrogen that does all of the dissolving and eating away at stuff. The rest of the acid molecule just dictates how easily it can do so, and what compounds does the dissolution create. We can interpret the strength of an acid on something called the pH scale. The lower the pH, the stronger the acid. For example, acetic acid has a pH of around 4 and hydrobromic acid around -9. Each level on the pH scale is 10 times stronger or weaker in comparison to its neighboring ones since it's a logarithmic scale, so hydrobromic acid is nearly 1 quadrillion times stronger than acetic acid, which is just crazy. To get an approximate reading of the pH value of a given thing, chemists often use these handy-dandy yellow strips, which turn different colors when exposed to different pH levels, often corresponding with the pH scale's colors, ranging from red to violet. Also, it is important to notice that the neutral pH is not 0 but 7, and it is the pH of, for example, water. Above 7, the pH becomes alkaline, or in other words, basic, and there is also a wide array of compounds having an alkaline pH, also known as bases. They, instead of getting rid of a hydrogen atom, most often dissociate into a hydroxide ion and have conjugate acids instead of bases, but apart from that, they work quite similarly to acids. They can actually be even more dangerous in some cases, but because people associate the word acid with bad and alkaline with good, such damp products as alkaline water exist. It does completely and absolutely nothing, but it's actually kind of funny how some people think that it has some magical healing powers. When you drink it, it all just gets neutralized in your stomach because there is also an acid in there. It is similar to the previously mentioned hydrobromic acid, but instead of bromine, it has chlorine, and it is naturally made by your body to help you digest food. This neutralization reaction is also something that was the basis for the previous experiment. In it, the baking soda, which is a weak base, reacted with acetic acid to form water by combining both hydrogen and hydroxide ions. It also formed a salt called sodium acetate by combining the conjugate acid and base of the two reagents, along with a ton of carbon dioxide, which is a gas, and it made all that foam in combination with dish soap. I chose this neutralization reaction just because of the carbon dioxide. Usually, if I were to use a different base, such as sodium hydroxide, the reaction would look much less spectacular, and that's how it usually is in the lab. If you think about it, it's quite sad that chemistry is not like in these stock videos with colorful solutions and happy, not sleep deprived, mentally sane chemists. But on the other hand, when something finally has a nice color, it's really cool. Cool. Anyway, after this whole introduction, you probably think, cool, but why would I need some weird hydrogen expelling chemical? Well, acids don't just react with bases, they have a ton of uses, and the easiest example of that is your body. As I said earlier, your body has a big sack of hydrochloric acid, also known as your stomach. Also, a lot of vitamins are acids, such as vitamin C, which is ascorbic acid, or vitamin B3, which is nicotinic acid. Also, in fruits there often is a lot of citric acid, so if you got that lemonade I talked about earlier, you are consuming some right now. It is also pretty interesting that we have a whole taste dedicated to acids, and it actually doesn't matter which acid it is, because you can make some good lemonade using dilute hydrochloric acid, which just kind of blows my mind. That's some good ass lemonade. There are also tons of acids used in factories, such as sulfuric acid, often dubbed the blood of industry. It is used in, for example, batteries, fertilizers, and dyes. I could go on and talk about, for example, nitric, phosphoric, carbonic, malic, or phthalic acids, but they all follow similar rules to the acids I talked about earlier, and I plan to dive deeper into them in future videos.
Do you see
Now, after
phallic
giving you a
acid?
brief overview of what acids
That's
are and how
that's
they
definitely
work,
not a
I want to show
acid.
you how one is made, and for that I specifically chose hydrochloric acid, more commonly known as muriatic acid. As I said earlier, it is the acidic stuff in your stomach. Apart from that, it has tons of uses in or outside the lab, and I myself have used it in countless videos for a variety of reactions, and making it is honestly quite interesting. You see, to do that, I will firstly need some chlorine, and if you know some extremely basic chemistry, you might recognize it from sodium chloride, commonly known just as table salt. The thing that makes your food taste better is actually a compound containing a part of a really strong acid and a powerful base, joined together through neutralization to create something completely harmless. Table salt is so safe because its components are really happy with their energy states and do not want to easily change places, which is good for cooking, but also means that I will have to use something really strong to get the chlorine out. That something just has to be a stronger acid in comparison to the hydrochloric one, because only then its conjugate base will replace the chlorine and join it together with a hydrogen atom. There are plenty of acids strong enough for this job, but by far the most accessible one is sulfuric acid. Now, before you dislike this video and write a comment about how it is impossible to get for a lot of people, I have some great news for you. You see, apart from the fact that you can quite easily extract it from car batteries as I showed in a previous video, since sulfuric acid has two hydrogens, it can form a quite special type of salts called bisulfates, which are much safer and accessible, and can function as its substitute in many cases. They definitely can be used here. When it comes to getting them, potassium bisulfate is often used as a cheap pH lowering agent for pools since it is acidic, but the way I am going to get it is through first making some nitric acid. Nitric acid, much like the sulfuric one, is a must-have in an amateur lab, and I make mine by combining together potassium nitrate and sulfuric acid followed by distillation. I won't get into much detail on this procedure here, but if you want to know more, you can watch my silver mirror video. Anyway, the byproduct of making nitric acid this way is a solid brick of potassium bisulfate, which I normally throw away, but now it will be just perfect for what I want to do. To start, I first have to get it out of this flask, and to do that, I filled it with a random amount of distilled water and got it onto this rusty electric stove, which did a really good job of warming it up, in the end leaving me with a nice and clear solution. While it was still hot, I quickly got it into a large beaker and then let it slowly cool back down to room temperature. This resulted in potassium bisulfate crystallizing out as these moldy looking crystals, which were rather squishy for some reason. I transferred about half of them, which corresponded to roughly 340 grams of potassium bisulfate, back into the flask using a spoon and a funnel, which was really messy, but I had to do it because I still had to add some other stuff, and otherwise it just wouldn't all fit. Anyway, with the potassium bisulfate ready, I could now start cooking up the hydrochloric acid, and for that I first had to get some table salt. I found some in a kitchen drawer and weighed out 145 grams of it, which I calculated to be more or less enough for all the potassium bisulfate. I then mixed it with the contents of the flask, and now with the mixture ready, I could start the reaction. Before I do that, however, I have to mention that you should never attempt this at home. Despite hydrochloric acid not being overly dangerous, it can still cause a lot of damage, so what I am doing here is for educational purposes only. Anyway, to get my product, normally I would just need to use simple distillation, but one of the more interesting properties of hydrochloric acid is that it is an aqueous solution of hydrogen chloride, which itself is a gas. This means that I will somehow need to trap this gas and lead it into water to make the acid, and I had to get really creative with assembling the setup, in the end coming up with this. I know that this whole thing looks kind of sketchy, but it should do the job. It consists of two main parts designed to make and capture the gas, with this nice piece of glass in the middle to prevent sagbag, which sometimes happens with these kinds of reactions, and it is just a total mess. To start generating the hydrogen chloride, I turned on my heating mantle, which initiated a reaction between potassium bisulfate and sodium chloride, producing hydrogen chloride along with sodium and potassium sulfates. Normally, this reaction would be carried out without the water, since a lot of the created hydrogen chloride dissolves into it instead of escaping into the apparatus, but then this whole thing would need to be kept at absurdly high temperatures required to melt the salts together, which my heating mantle just can't reach. Fortunately, some gas started being produced and escaped into the distilled water flask. However, this was still mostly air,
That
meaning
works.
that nearly all of the hydrogen
They did
chloride
not
was
like that.
dissolving into the water present in the boiling flask, which now got very yellow for some reason, and I had to come up with a different plan of getting my hydrochloric acid from this mess. I thought that since I already
Are you
had it in the
super
flask,
sensitive?
I could just distill it over, so I assembled a distillation setup in place of the previous one and started heating the flask up real hard. At first, a lot of some yellow liquid started coming over, which was probably just some really dilute hydrochloric acid. I really have no idea why it was yellow, because even if there was some residual nitrogen dioxide being created, it should dissolve, leaving me with a colorless solution. So I guess that the chemistry gods are just messing with me. Anyway, I continued the distillation, periodically draining the distillate into different beakers. I also had a gas trap set up, and this time there was some hydrogen chloride coming over, indicated by these hardly visible waves, nearly bubbles. I continued the distillation until there was no more stuff coming over. And before proceeding, I have to quickly tell you about an online chemistry supply shop, BM Chemistry. BM Chemistry sells many chemicals, glassware, and lots of other stuff, so if you are interested, there is a link to their page in the description. Anyway, the resulting distillate was orange this time, which is really weird. I could also see some nitrogen dioxide gas in the apparatus, which meant that there was some unreacted potassium nitrate from making nitric acid present. This could also mean that the distillate I collected is made purely of nitric acid, but I can quickly rule that out since it readily dissolves
Oh,
aluminum foil,
they're just sitting
which
around.
normally is resistant to nitric acid. Anyway, all the fractions obtained through the distillation are acidic, meaning they contain at least some acid, but to see how much, I tested how each one of them reacts with baking soda, and to be honest, most of them are quite weak. They might be useful for something, but I just decided to keep the last and strongest fraction and get rid of the other ones. When it comes to its concentration, I measured it by checking its density and using this helpful online chart. It came out to be around 36%, which is incredibly good and almost as high as it gets. When it comes to my acid's purity, apart from the orange coloration, which makes it look like apple juice, it should be really quite pure and suitable for a lot of reactions. It's incredibly cool that I managed to make some really strong acid from just some random pool chemical and table salt. The whole process is a really good demonstration of the properties and behaviors that apply to many acids, and overall I am really happy with how it went. Now, for some experiments with my acid, I decided to first test how it reacts with proteins. So I got this egg white, and upon combining it with the acid, you can see that it becomes white, looking like it's cooked. This nicely shows what it would do if you drank it, for example, and you might think that you can do it since it's already in your stomach, but it is specifically designed to be resistant to it, while your throat is not. Anyway, one more thing that this acid is good at is dissolving stuff. It reacts with metals like iron and aluminum, producing hydrogen gas, and their chlorides, which are often really colorful and useful chemicals. And now, for a fitting end of this journey, I can react my hydrochloric acid with some sodium hydroxide, which through a neutralization reaction creates the almighty table salt. This almost poetically symbolizes how you can waste hours of your work, but it also probably has some deeper connections to the cycle of life and all that stuff. However, this is not a philosophy channel, and it's just quite cool to see how different chemicals interact with each other. Anyway, I hope that you enjoyed this video and learned something from it. If you did, you can like and subscribe to my channel for more chemistry content. Also, I would like to thank my amazing Patreons for their support in making these videos possible. If you would also want to support my work and gain access to exclusive content, feel free to also become a Patreon. And see you guys in the next video.
trip safety check at Les Schwab Tires. It's free.
Hi guys, welcome to Amateur Chemistry. So, plastic bottles. If you think about it, they are kind of everywhere, since nowadays having a drink of almost any kind involves the use of one. Now, the average person just throws used plastic bottles into the trash, not thinking much about them, and honestly, that's exactly what I did until very recently. You see, having more time to think about the chemistry around us because of this amazing channel, I progressively became more and more fascinated with how this seemingly simple plastic bottle is actually a treasure trove of useful chemicals. The plastic most bottles are made of is something called polyethylene terephthalate, or PET for short, and apart from giving me one more reason to pet my cat, this name tells me the exact juicy chemical composition of this plastic. It's made of long chains of this thing here called a monomer, and the plastic polymer it forms contains a bunch of these seemingly random hexagons. Now, they may seem that way to you, however, when I first saw them, my chemist neurons activated, since this is literally the structure of this little goober called benzene. Benzene has a special place in the heart of every chemist, be it for its rich history, the thousands of things it can be used for, or its quite potent carcinogenicity, and I think that every chemist agrees that it's good to have it in the lab. I always wanted to have some, however, because of it being literal cancer juice, many countries, especially in the EU, don't really like it. They actually kind of hate it, in fact, and to this day I haven't been able to find affordable benzene anywhere. This brings me back to the structure of PET, which contains a really big amount of these benzene rings, and one day I had this wild idea of somehow tearing them out and turning them into homemade benzene. I hope that I painted you a good picture of why this would be kind of revolutionary for me and would also make a hell of a good project for the channel, since this is literally recycling on steroids. That's why a while ago, not really knowing what I am getting into, I set off on a journey to turn plastic waste into one of the coolest molecules, and since not many people seem to have attempted this before, I wanted to see if it could make some decent benzene. Anyway, before figuring out how I am going to forcefully tear through some plastic to steal its benzene, I first have to get some of it. This was quite easy, since after only like 2 weeks of saving every bottle I drank from, I collected 20 of them. They make for some good bowling pins and should contain around 400 grams of plastic, which is the scale I want to work on. I figured that even if my yield is trash, this much plastic should be enough to get a good amount of benzene, and before doing any chemistry, I had to prepare it a little. By prepare, I mean remove these annoying European Union caps, which are made of a different plastic, as well as compact the bottles a bit, since they currently take up way too much space. I want to grind them down as close to a powder as possible, and to start, I whipped out this comically large knife with the pointy part broken off for some reason. It made for a great tool in removing the tougher top and bottom parts of the bottles, leaving behind just the thin shells. To pulverize this mound of decapitated battle corpses, I wanted to use a blender, however, the plastic turned out to be weirdly hard to grind. It's kind of soft and brittle at the same time, and the blender just wasn't having it. I mean, I even tried blending it underwater, which gave no good results. I could spend hours developing some advanced plastic grinder and tear through the bottles in no time, but being the patient person wannabe I am, I turned to using these puny office scissors and some elbow grease. It took me like 3 hours, but I managed to turn all 20 bottles into these label-less clippings, perfect to be used in some chemical reactions. They only weighed 200 grams, however, so to squeeze more plastic out of the bottles, I also processed their tougher parts. As expected, this was a big pain, and the only tool capable of splitting them was this massive tree pruner. It allowed me to finally reach my target 400 grams of cut PET plastic, and I also had to use a few of these darker colored bottles since the 20 I started with weren't quite enough. Anyway, with this very hard-earned box of laboratory-grade plastic ready, I could now finally extract the benzene from it. There is unfortunately no single chemical reaction that just magically does that, and the best approach to take here is to slowly weaken the plastic. This basically means breaking progressively stronger bonds in its structure, and the best bond to start with is this one. It's something called an ester bond, and it's also the reason why this plastic is often called polyester. Breaking it would make the polymer structure completely fall apart and quote-unquote de-shield the benzene. The resulting benzene-containing compound will then have a much easier time turning into pure benzene, which is exactly what I want. Breaking the ester bonds of PET isn't easy, and to do it reasonably quickly, I have to use some really angry chemicals. The one I am going to use is something called sodium hydroxide. It's often used for things like drain opening, and it's corrosive enough to eat through polyester reasonably